Hi, I'm Tsung-Wei from the University of Utah. My research makes parallel computing easier to handle, so you can quickly speed up your application performance. Today, I'm going to show you Taskflow, an open source C++ programming system that can help you quickly write parallel and heterogeneous programs. You probably already know parallel computing is critical to advance your application performance. For example, a single threaded machine learning program can take several hours to finish, but it can be reduced to only a few minutes or even a few seconds if we are able to run it in parallel. That's the power of parallel computing. By leveraging many core processing units, we are able to speed up the performance by several orders of magnitude. However, writing a good parallel program is very challenging because you need to deal with many difficult technical details, such as standard concurrency control, task dependency, scheduling, and data race. And many CPP developers have a hard time in getting them right, especially for those who do not have that much experience in parallel computing. So it is really important for the library to make sure developers can focus on their application level development as much as possible, instead of dealing with all these difficult parallelization details. The Taskflow project is trying to offer the solution to this. We address the following question. How can we make it easier for CPP developer to quickly write parallel and heterogeneous program with high performance and simultaneous high productivity? And by high performance, we mean the program has to run fast and scale to many core processing units, including CPU and GPU. By high productivity, we reduce the time it takes to implement the program. Let's take a look at Hello World example in Taskflow. Suppose we want to do four things, A, B, C, D, each representing a function or a task. A has to run before B and C, D has to run after B and C. So when A finishes, B and C can run in parallel. When both B and C finish, D can start. This is how it looks in Taskflow. Only 15 lines of code to get a parallel task execution, and this is all you need. You create a Taskflow object to manage a task dependency graph, and then you create an executor that manages a set of worker threads to run task flows. Here we use the method in place to create four tasks in terms of CPP lambda and assign them to A, B, C, D using the structure binding in C++ 17. To build out dependency, we use precede to force A to run before B and C, and succeed to force D to run after B and C. Finally, we submit this task flow to the executor, and it returns a future where we can wait on it to finish. At this moment, I believe many of you can fully understand what the code is doing, and the code explains itself through an expressive graph description language. Here is how I'm going to do in the rest of the talk. I'm going to show you how to express the parallelism in the right way by starting with the motivation behind Taskflow and the application we target. Then I will present how to use Taskflow to parallelize application and give you a rough idea about our work-sticking scheduling algorithm. Next, I will demonstrate some real use cases of Taskflow and show you how it can boost the performance in large-scale parallel application. Finally, I will share with you some of my experience in using C++ to parallelize large-scale applications so we can enhance C++ to make it more amenable to heterogeneous parallelism. Let's start with number one. I'm going to show you the motivation behind Taskflow so you can express your parallelism in the right way, depending on application. In the past, I've been developing parallel CAD software for VLSI systems. CAD stands for Computer-Aided Design. It is a software method to help people design integrated circuits, or IC. You start from a high-level description of the hardware component and take this source to the CAD software, and the CAD tool will generate a bunch of netlists and synthesize it then to the physical layout. And you can tap it out to get a final chip that lives inside your smartphone, computer, and all electronic devices. This is a seriously complicated process. For example, if you take a look at layout generation process, it requires partitioning the graph, circuit graph, of billions of nodes, floor plan placing millions of cells in a very small area, routing trillions of wires to establish the signal connection and analyze the timing of all these billions of components. And the resulting computational task graph in terms of encapsulated function call and task dependency can easily go up to millions of tasks with cycle, dynamic control flow, irregular computational pattern that takes several days to finish. So we want to answer a question. How can we write an efficient CPP parallel program for this monster computational task graph that has millions of CPU, GPU dependent tasks along with algorithmic control flow? Because building a parallel CAD tool is very complex, we want to find a programming system that can assist us with the implementation and deployment of parallel CAD algorithm. To this end, we have invested a lot in existing parallel computing systems, including P-Thread, OpenMP, CPP Thread, Intel TPP, SQL, StarPU, and low software from the ECP project by Department of the Energy, such as Cocos, Raja, and Parsec. Unfortunately, we found very few of them can meet our purpose. The reason is as follows. We summarize two big problems of existing tool in this slide. First of all, our problem defines very complex task dependencies. For example, analysis algorithm need to compute a circuit network of billions of node dependencies. That is, the resulting task graph in terms of model function code and their dependency can go very irregular and millions. But the problem is, most of the existing tools are good at loop parallelism, but they are not very strong in expressing heterogeneous task graph at this large scale. For example, OpenMP is very good at regular parallel for loop, but it's not very efficient for irregular parallelism. Second, our problem has very complex control flow. For example, optimization algorithms make essential use of dynamic control flow to implement various computational patterns to carry out combinatorial optimization and analytical method. And the problem is, most of the existing tools require you to describe a parallel workload in a direct acidic graph, and the graph cannot have cycle, and they do not anticipate cycles or conditional dependencies. The result of that is lacking end-to-end parallelism, because you need to partition your workload or algorithm across the control flow, and you synchronize your parallelism at a decision-making point. To better understand this problem, let's take a look at an example of an iterative optimization program. The program has 4 tasks and start with an init task that initialize the data structure. Then they enter the optimizer task to perform optimization. For example, solving a linear system using a GPU. Next, it moves on to the converge task to check if the optimization converge. If yes, it goes to the output task and stop. Or otherwise, it moves back to the optimization task again. And you can see this problem has an iterative control flow. And doing this in a single-threaded setting totally makes sense, but it is very difficult to do in a parallel environment. Maybe we should ask this question. So how can we describe this workload of dynamic control flow using existing tools, such as OpenMP, TPP, StarPU, SQL, or Cocos? And what about the situation we have millions of such tasks that overlap with each other and each has a dynamic control flow? What about a way to describe them with end-to-end parallelism instead of partitioning the parallelism across the control flow or synchronize your parallelism at each iteration? After several years of research, we arrived at a key conclusion. We need a new CPP programming system. And the takeaway here is, while designing parallel algorithm is non-trivial, what makes parallel computing an enormous challenge is the infrastructure work of how to efficiently express dependent tasks, along with an algorithmic control flow and scheduling across heterogeneous computing resources. That is the key motivation to support Taskflow project. We want to strike a balance between 3 aspects: performance, productivity, and portability. We want to maximize the performance compared to handcrafted solution. We want to maximize the productivity compared to handcrafted implementation time. And we want to maximize the portability by leveraging the power of modern CPP. More importantly, we are not to replace anything. We are not to replace existing tool, but we are trying to address the limitation on task graph parallelism. And we keep our interface as compatible as possible so we can reuse their facilities. Because we believe only this we can deliver complementary advantage to advanced CPP parallelism. Next, I'm going to show you how we can use Taskflow to describe parallelism using a task graph in your application. Taskflow is a programming system, and I cannot present a programming system without showing you some real code. In the rest of the slide, there will be a lot of intensive coding example, and I hope this will not destroy your beautiful morning. Programming is quite subjective, so many arguments I'm going to present are based on my personal opinion. No offense, no criticism. It is all about C++ from both the users and the researchers' perspective. Taskflow defines 5 task types: static task, dynamic task, CUDA flow task, condition task, and module task. Static task is the most basic task type in Taskflow. It takes a callable object and runs it. A dynamic task lets you spawn a task dependency graph during the execution of a task, so you can do some dynamic parallelism. A CUDA flow task lets you describe a GPU workload in a task graph and offloads it to a GPU. A condition task lets you integrate control flow into a task graph, so you can describe end-to-end parallelism. A module task lets you compose a large task flow graph through smaller task flow that are easier to optimize. So in this Hello World example we have seen before, the 4 tasks, A, B, C, D, are static tasks. They simply take 4 lambdas, callable object, and run them. Those are static tasks. The same Hello World example here, but written in OpenMP's tasking interface. OpenMP is a language extension to describe parallelism using compiler directives. It is a very popular programming library. Almost all people start with to learn parallel computing. In this example, we use OMP's task syntax to create 4 tasks, A, B, C, D. And then we use a depend clause to specify the outgoing dependency and incoming dependency for each of the 4 tasks. For example, in task A, we need 2 variables, A, B, and AC, to capture the constraint between A and B and A and C. And we do the same thing for the other 3 tasks. The code itself is not that complicated, but it is static. You need to explicitly define everything such that compiler would know how to generate a dependency. Another big problem is you are responsible for a proper order of writing tasks, and the order has to be consistent with the sequential execution. Because when you compile this program with a different compiler where OpenMP has to be disabled, everything falls back to sequential execution. And you gotta make sure the order you roll these tasks is not breaking the dependency when they run in serial, right? So you need to figure out a topological sorting order of the graph. And this makes it very difficult to describe upfront parallelism, especially when dependencies are not known at the programming time. Same example again, but written in Intel's threading building block library, or TBB for short. The TBB is a general-purpose object-oriented parallel programming library in CPP. It has been used by the industry for many years. The idea of TBB is very similar to Taskflow in a sense it describes dependent tasks using a flow graph. You create a flow graph, then use the monster class continue node to create 4 tasks, A, B, C, D. And then you use another big template, continue message, to describe dependency among A, B, C, and D. Finally, you identify the source task, which is task A in this example, from your graph and insert A into the scheduler. So the scheduler knows where to start the execution. According to our research, TBB has really excellent performance, especially when you are running an Intel architecture. But it turns out many API defined by TBB is very complex, and even though they are very powerful, I would say the main drawback is mostly on the ease of use standpoint in terms of simplicity and expressivity. Final comparison is written in Cocos. Cocos is a parallel computing library that has recently gained much attention from the community. It's part of the exascale computing ECP project under the Department of Energy. Cocos leverages CPP-style future object to handle task parallelism. As far as I know, at the time of this presentation, Cocos does not support CPP lambda. So in order to create tasks, you need to define a task function of fixed memory layout. Everything is based on C++ future object, and you launch a task asynchronously and get a future, and then eventually will hold the result to that task. Task dependency are described in terms of aggregated future object, where you specify when one future finish, another can start running. And there is a lot of overhead happening during this shared state control. Also, we need to explicitly tell the Cocos runtime all the scheduling detail about the task dependencies using the function host spawn. And there are more scheduling code which are not able to present all the code at a single page. So it turns out Cocos is very powerful in describing asynchronous tasks, but it's not very efficient in large task graph due to the overhead of many of these shared state control. And also, it is not as expressive as other library if you want to use it to describe a task graph. Of course, what I presented to you was my personal interpretation. It can be biased. So I took advantage of being a university faculty and gave a programming assignment asking students about 100, and how would you like to express this slightly more complex task graph of 10 tasks, 15 dependency, and vote for the following 5 different libraries: Taskflow, OpenMP, TBB, Cocos, and StuThread. I did not tell them I'm the author of Taskflow, otherwise the vote will be even more biased. But what I'm trying to discover is how C++ learner think about this parallel computing library, especially for those who are learning CPP to use parallelism in their application. And this is how it looks. About 74% like Taskflow. And more importantly, the number one concern they have is my application is already very complex, and I don't like the parallel programming library to become another burden to parallelize my application. So this is the goal we need to pursue. We need to let developer focus on high-level algorithm as much as possible, instead of wrestling with many parallel tasking details. The previous example was static tasking. You decide a task to spawn at the first level of the graph. We can do dynamic tasking. You can spawn a task dependency graph from the execution of the task using a dedicated interface subflow. In order to create a subflow, you place a lambda with an argument on subflow, and you describe another task dependency graph in that subflow. For example, here we create another task dependency graph from the execution of task B, and the subflow has 3 tasks, B1, B2, and B3, where B3 runs after B1 and B2. So, when the scheduler finishes A, you start running B, and then spawn another task dependency graph inside the subflow and runs B1 and B2, and then B3. Eventually, the subflow joins its parent task B, and then we move on to task D. Subflow can be nested. You can create a subflow from another subflow and so on. And this is an example of a task graph that finds the 7 Fibonacci number using subflow. And this is a very common example for most of the parallel computing library to show recursive parallelism. Fibonacci number is a series of numbers where each number is the sum of the previous 2 numbers, and it can be done with recursive parallelism. You can offload a task to GPU. We manage heterogeneous CPU-GPU tasking through a closure-based interface, CUDA flow. A CUDA flow is a task associated with a CUDA graph, which is a new feature in NVIDIA since CUDA 10. A CUDA flow is very similar to subflow. It takes an argument of CUDA flow, and that will be created during the execution of that CUDA flow task. Within this CUDA flow, you describe multiple GPU work, such as data transfer and kernel in a task dependency graph, rather than aggregated operation using CUDA stream. In this case, we have two copy tasks to move X and Y from CPU to GPU. And then we have a kernel. We have a kernel task that offloads the computation of a written kernel onto a GPU. And when the computation finishes, we create another two copy tasks to get the data from GPU. Of course, if you are using unified shared memory, you don't need this copy task. You can simply launch the kernel and build up a dependency between kernels. By leveraging the power of CUDA graph, we launch an entire GPU task graph in a single kernel code instead of multiple ones, so we can largely reduce the overhead. And when you finish the description of the GPU task graph, Taskflow will automatically transform the task graph you describe and transform it into a CUDA graph. So when you finish the description, and you can pipeline the entire CUDA flow with other CPU tasks or other CUDA flow. And this is very important because the CPU, GPU programming always involves some data transformation task, and that comes with an expensive cost. Without a suitable task graph interface, it's very difficult to express this overlap, and that we can take the most advantage of CPU, GPU computing. For example, in this case, I created LKX on CPU and another CPU test on LKY, and both can overlap. And when they finish, Taskflow will fork a task graph to launch the CUDA flow. The design of CPU-GPU heterogeneous tasking has three key motivations. First, our closure enables stateful interface. We can capture data in reference to marshal data exchange between CPU and GPU tasks. This is very important for graph parallelism because when everything is formulated as a task dependency graph, we need to make sure the computation result of CPU task is visible to GPU task and vice versa. For example, CPU tasks may compute the data size, allocate the memory, and then GPU tasks know how to set up the kernel parameter. So you gotta make sure the result you compute from the CPU tasks are visible to GPU tasks. So we can describe everything in a single graph entity. Second, our closure interface can hide implementation detail judiciously. It provides a lightweight abstraction over GPU implementation. By default, we use CUDA graph due to its excellent performance, much faster than CUDA Stream, OpenCL, and SQL, based on our profile. Also, this closure interface is extensible to new accelerator type. For example, we may define SQL flow, OpenCL flow, TPU flow, or FPGA flow, where we can tailor a graph interface for each of the accelerator type. And one thing I would like to highlight is Taskflow does not simplify kernel programming, but we focus on CPU, GPU tasking that affects the performance to a large extent. Same reason for data abstraction, so Taskflow can complement many of the existing kernel programming systems. Conditional tasking is a powerful interface to enable dynamic control flow, and we believe this is one of the key features that stands out Taskflow from other libraries. You can create a condition task that returns a value indicating the next immediate successor to run. Of course, you need to satisfy certain rules. You cannot jump to anywhere you want, and we do have a spatial scheduling policy for you to follow, and we'll explain it later. In this example of iterative optimization, we have seen before, I created a task graph of 4 tasks: init, optimizer, converge, and output. Init task initialize the data structure we need for optimization. Optimizer task launches the optimization routine, such as solving a linear system in the matrix form. Converge task check if the optimization converging, and it forms the cycle back to the optimizer if we haven't reached a convergence point, or move on to the output task and stop. The converge task here is a condition task, and it precedes 2 tasks, optimizer and output. With this order, when it returns 0, when the converge condition task returns 0, the scheduler will re-execute the optimizer task again, or it moves on to the output. And we specify this in the return value of this condition task converge. And you can see in this example, there are ultimately 4 tasks ever created. You describe this iterative workload in a whole graph entity. There's no need to partition your graph and synchronize it at each iteration. Condition tasks can handle more complicated scenarios, such as nested and non-deterministic control flow. In this example, I create a task graph of 5 nested cycles. Each green task is a condition task in this figure. It does nothing but flips a binary coin to decide the next path. Either move on or go back. If it returns 0, it moves on to the next task. If it returns 1, it goes back to the first condition task and start everything from the scratch. There are 5 such tasks to flip a binary coin, so you can infer that the average number of condition tasks you need to go through before reaching the task end is 32, because we got a probability of 1/2 at each condition task for us to move on. And similar to the previous example, ultimately, we use only 5 condition tasks to model this nested, non-deterministic task execution. Even though we may end up with 32 execution, in average, the scheduler will reuse these 5 condition tasks. Now let's ask the question, how do existing framework handle condition? Many of them are based on direct acidic graph and they do not allow cycle. And I'm not talking about a cycle you have in pipeline, but a generic interface for you to describe control flow in a parallel task graph. The most common solution is to expand the task graph across fixed length iteration, right? For example, if you happen to know a loop condition is going to span 5 iterations, you can unroll the task graph. And the result of that is, of course, increased graph size and memory consumption. But what about a loop of unknown iteration, like non-deterministic conditions we saw in the previous slide? You may spawn dynamic tasks, executing an if statement on the fly to decide the next execution path. But that solution often gives you a rather complicated implementation with recursive parallelism. In fact, according to our research, for generic condition, existing frameworks suffer from exponential growth of coding complexity. Our tasking interface is composable, and this is the key element to improve programming productivity through composition. You can create multiple task flows, each representing a portion of your parallel decomposition strategy that is easier to optimize at a smaller scale. Then you can assemble these task flows, smaller task flows, to form a large task flow that compose correctly and efficiently. In this example, we create 2 task flows, F1 and F2. F1 has 2 tasks, F1A and F1B. F2 has 4 tasks, F2A, F2B, F2C, and the module task composed of task flow F1. And you can do this composition in just 1 line of code using the method compose of. So if F1 here has 2 static tasks, F2 here has 3 static tasks, the runtime will start from F2A and F2B and then move on to the module task that spawn the task dependency graph described in task flow F1. And then we run F1A, F1B, and then when they finish, we go to F2C. So this is how composable tasking works. We can partition a large task flow into several smaller task flow. They are easier to compose and optimize individually. The biggest advantage of task flow is everything is unified. You use the method in place to create a task, whether it is a static task, dynamic task, CUDA flow task, condition task, or composition. And then you use the single method precede to relay the dependency between tasks. And you can create a really, really complex graph that combines all the different task type and integrate control flow into your task flow. So everything runs end-to-end. And our schedule will perform end-to-end optimization on runtime, energy efficiency, and throughput. This is another example of using task flow to describe k-mean clustering using CPU and GPU tasks. K-means is a clustering algorithm that tries to find the best K-centroid among a set of points. It is iterative. You have a CPU, GPU task running iteratively to compute the K-centroids. Here, we use a single task flow to represent the entire K-means workload. We have one CUDA flow for performing the host to device data transfer, and then we have another CUDA flow to compute to find the best K-centroid of the current iteration. And then we define a condition task to model the iteration. And when the iteration converge, we have another CUDA flow for performing device to host data transfer. So you can see everything is unified. We need only a single task flow that can represent the whole K-mean clustering algorithm of iterative control flow. We have learned the core programming model of task flow to describe a parallel program using a task dependency graph. Being a CPP developer, not only do we care about the expressivity of the library, we also need performance. And that needs efficient scheduling algorithm. So I'm going to show you our scheduling algorithm and how we can submit a written task flow with control flow into the execution engine executor. An executor is where you submit a task flow to execute tasks defined in that graph. An executor manages a set of worker threads to run task flow. All execution methods are non-blocking and thread safe, so you can pretty much do whatever submissions you want. Let's take a look at this example. Suppose we have three task graphs: task flow 1, task flow 3, and task flow 3, or task flow 2 and 3. And we have an executor, and we define several methods to run the task flow. For example, you can use the method run to run a task flow by once, or run n to run a task flow by n times, or run a task flow until a stop predicate becomes true using run until. For example, in this line, I use the run until method to run task flow by 5 times. In addition to running a task flow, you can launch a task asynchronously using a SDL-style asynchronous function call. And this makes it very handy if you want to create a task on the fly with no dependency. And the scheduler will autonomously execute all those tasks and decide which worker thread runs which task. Our scheduling algorithm has 2 levels, task level and worker level. At the task level, we decide how tasks are in queue to the wait list under control flow. At the worker level, we decide how tasks are executed by which worker. And the goal of task level scheduling is threefold. We want to ensure a feasible path to carry out the control flow. And the key point here is we want to avoid task race under static and conditional execution so we can maximize the capability of a conditional tasking. For example, you can describe a cycle in a graph, but it is only schedulable when only one worker enters that cycle at any time. Otherwise, the task will be raised by multiple workers. On the other hand, the goal of worker level scheduling is to optimize the execution performance by leveraging work stealing to dynamically balance load. And because the available parallelism changes from time to time, depending on the point you are in the task graph. For example, you might have 1 task at this time and 4 tasks at another time. And next time you rerun the task flow again, and all the situation change. So we need to adapt the number of worker threads to available task parallelism at any time, rather than keeping them all busy, so we can maximize the performance, energy, and throughput. In order to schedule tasks under control flow, we define 2 dependency types, strong dependency and weak dependency. A weak dependency is the dependency coming out of a condition task. Others are strong dependency. For example, the dependency from the, in this example, from the converge task to output and optimize the task are weak dependencies because they are coming out from the condition task. And the task level scheduling flow is as follows. When you submit a task graph, it starts with a task of no dependency, including both strong and weak dependency. In this case, we will start from init task because init task has no dependency. So the schedule will start from init task. When the scheduler runs a task from the queue, It branches the execution depending on the task type. If it is a condition task, it invokes the callable, and get a return value from the condition task, and jump to the pointer successor. If it is not a condition task, it invokes the callable, decrement a strong dependency of all its successor by 1, and then enqueue low successor whenever dependency are met. And you can infer that without condition task, if you remove the condition task part from this scheduling flow, the scheduling falls back to the normal direct acyclic graph scheduling. Condition task is very powerful for you to describe control flow in a task graph, but it is also easy for you to make mistake. The following example shows 2 common pitfalls of using condition tasks. In the first task graph, we have a condition task A, and it precedes 3 tasks, itself, task B, and task C. The problem of this graph is it won't get scheduled because there are no tasks for us to start with. Remember, we always need to start with a task of no dependencies, including both strong and weak dependencies. There are no such tasks. Fix number 1 is to add a source task, S. So we can have it precede task A, then we can start from the source task A, S. And the second pitfall here is you may run into task race. Both E and C has no dependencies, right? So they can both start at the same time. When E finishes, it enqueue task D. And at the same time, if task C returns 0, then task D is in queue. Then the scheduler may race on task D. To get it fixed, we need to add an auxiliary node between task D and C. And this, in fact, is to tell the scheduler that the task D is conditioned by 2 situations. Both E finishes and C returns 0. Indeed, this totally makes sense if you think about it as a normal single-threaded control flow, because we will not run task D until both conditions are true. And for now, it is the user's responsibility to ensure a task flow is properly conditioned. Of course, in the future, we may add some help check API or algorithm or functionality to help you diagnose potential pitfall of a written conditional tasking. At the worker level, we adopt the work stealing to run tasks. This is a masterpiece of work. We have spent a lot of effort on the research, and unfortunately, I won't be able to cover all the detail, but I will try to give you an impression about how it works. So, what is work stealing? In a nutshell, it is a dynamic scheduling algorithm. I finish my job first, and then I steal a job from you. So we can improve the performance through this decentralized dynamic load balancing. When a worker thread drains out its task queue, and it tries to get some more tasks from other workers. And this is the essential point of work stealing. And there is an excellent talk about the work stealing at CPPCon 2015 by Pablo Halpin, and you are definitely encouraged to watch it for more details. There are 3 challenges we tackle in the worker level scheduling. Challenge number 1, distinct CPU-GPU performance trait. And we solve it by keeping a different set of workers per heterogeneous domain. For example, CPU workers for CPU tasks and GPU workers for GPU tasks. And the reason is we need to separate the execution between CPU and GPU tasks because they have different execution time. Mixing them together can cause the problem of unpredictable delay. Challenge number 2, available task parallelism keeps changing during the execution of task graph, right? The available tasks you may have at any time are all different. Time point 1, you may have 4 tasks, and the next time you may have 10 tasks. And we rerun the program again, the situation change. It all depends on the task graph structure. And this is also related to the next challenge number 3, that we need to properly control the worker they are making steal attempt. Because in the work stealing loop, you may fail to steal tasks, especially when multiple workers are stealing tasks from the same worker. Only one can make it. So we need to properly control the wasteful steal that may potentially degrade the performance. And we solve these challenges by keeping an invariant that try to balance the active workers with available task parallelism at any time during the graph execution. And we bring worker to sleep when we don't have many tasks to do, and wake up workers to run tasks when tasks are abundant. And this is the scheduling architecture of Taskflow. There are two domains, one for CPU workers and one for GPU worker. Each domain keeps a set of workers to run tasks of the same domain. A worker can only steal tasks of the same domain from the other worker. When you submit a task graph, it goes through a globally shared task queue, which can be either the CPU task queue or the GPU task queue. And then the workers start to steal tasks from the shared task queue and execute that task, including the following successors spun from that task. And in this architecture, our schedule is generalizable to arbitrary heterogeneous domain. We have understood the scheduling algorithm in Taskflow. Next, I'm going to present to you some of the results we have obtained from applying Taskflow to real application. This performance data is another big thing users really care about. The first experiment I'm showing you here is micro-benchmark, and the purpose of micro-benchmark is to demonstrate a pure tasking performance without too much bias from the application algorithm. And we randomly generate a task graph with even CPU-GPU tasks, and each CPU task performs a constant time operation, AX plus Y, and that is a very famous sexy pi operation with 1K element. And each GPU task does the same thing, but with 10K element. We compare Taskflow with four very popular parallel programming libraries, TBB, StarPU, HPX, and OpenMP. And we are interested in the two questions. So what is the turnaround time to program? And what is the overhead of task graph parallelism? So table 1 summarizes the programming cost. We use a very famous tool, SLOC count, and they can analyze your source code in terms of lines of code, numbers of token, cyclomatic complexity, and people and costs that may be involved, in potentially in developing your program. And we can see from this table, Taskflow has the least cost across all, reported by the SLOC count. On the right table, we summarize the overhead of task graph parallelism. Describing an application in a task graph is convenient, but it comes with some overhead, right? This overhead is very important for us to decide the granularity of tasks when we want to use it. And we can see both Taskflow and TBB are quite good. And Taskflow is a little bit faster in creating a task and dependency. It's about 30 to 40 nanoseconds faster. But the size of the task defined in Taskflow is a little bit larger than 1 TBB or TBB. It's about 272 byte and 136 byte for TBB. But when graph size becomes as large as 40 tasks, the overhead is less than 1% of the total execution time. Let's take a look at performance. The top four figures show the performance on runtime, memory, energy, and power. Blue line is Taskflow, red line is TBB, light blue is StarPU, black line is HPX, and brown line is OpenMP. In terms of runtime, Taskflow is faster than the others, and that is due to our scheduling algorithm, which we always adapt the workers to available task parallelism for dynamic load balancing. And this also translates to better energy and power efficiency, where we major using the Linux kernel provider because we are able to use the minimal threading resources to finish the workload. And in the workload splitting loop, we can control the number of Westfall steal. The downside of that is, of course, higher memory consumption. And Taskflow consumes a little bit higher memory than the others. It is about 100. If the graph size is as large as 1K, 10K, it's about 100 megabyte higher than the others. And another attribute to this is our scheduling architecture, because we have a separate data structure for each domain, CPU and GPU. So the second experiment I'm going to demonstrate is a real application on machine learning. Here we try to compute the inference of a very large deep neural network. It has 1920 layers of DNN, each of 6 5536 neurons. The entire network can take up to 50 gigabyte memory. And this is also the problem given by the IEEE HPC high performance computing community as their yearly graph challenge problem. The figure here is a partial task flow graph of 4 CUDA flow, 6 static tasks, and 8 condition cycle for this machine learning workload. Each CUDA flow contains thousands of GPU tasks because the network is too large to compute using a single kernel. If you launch these thousands of GPU operations one by one using CUDA stream, the overhead becomes very, very, very significant. And because the network is very large, the advantage of task graph parallelism starts to come out. This slide shows the performance data where we compare Taskflow with TPP and StarPU because they both support task graph parallelism explicitly. And this machine learning workload is iterative, and we use condition tasks of Taskflow to model the control flow. However, TPP and StarPU do not support control flow, so we unroll their task graph across iteration found in hindsight, and we implement CUDA graph for all the library. The figure in the middle over here shows the runtime and memory at different CPU and GPU number. Again, blue line is Taskflow, red line is TPP, and library is StarPU. In general, you can see Taskflow is much faster than TPP and StarPU. It's about 2x faster. Memory is about 1.6x less because we use condition tasks instead of unrolling the graph across iteration. And there is no explicit synchronization or client-side partition across the control flow by using condition tasks. The second application I'm going to show you is a VLSI placement workload we have applied Taskflow to solve. And VLSI placement is a very important step in the circuit design flow. It optimizes the cell location on the chip. A cell is essentially a gate, OR gate, NOT gate, AND gate, and so on. In modern design, there are millions of such cells in a placement optimization that can take several hours to finish. And this is an optimization workload, and it makes essential use of dynamic control flow to describe iteration. To speed it up, we implemented a GPU accelerated algorithm that leverages CUDA flow to offload tasks to GPU and condition tasks to capture the iterative optimization control flow. Here is a partial task graph of 4 CUDA flow, 1 condition cycle, and 12 static tasks that describe a tiny fraction of the graph. And keep in mind, the entire graph is much larger than this. Again, we compare the performance of Taskflow against TPP and StarPU because they both support task graph parallelism. And we measure the performance in terms of runtime, memory, and power consumption. In these 3 figures, blue line is Taskflow, red line is TPP, and library is StarPU. On the top left figure, the runtime plot, you can see Taskflow is a bit faster and the difference starts to increase when the problem size becomes larger and larger. All algorithms saturate at about 16 CPU cores, but before that, we found Taskflow is always faster. And this placement optimization workload is iterative, like we say, so we use condition tests in Taskflow to model the control flow. But for TPP and StarPU, we have no choice but to unroll their task graph. And that comes at the cost of increased memory. And you can see the memory difference between Taskflow and the other implementation is very, very large. And this, of course, can affect everything get together, can affect your energy consumption. So you can see in the power data, Taskflow is much better than the others. I would like to summarize this result with a key takeaway. Parallel programming infrastructure is just as important as the parallel solution itself. Different models are going to give you different implementation, and the parallel code algorithm itself may run very fast. But the parallel computing infrastructure you use to support that algorithm may dominate entire performance. And this is especially important when you consider heterogeneous workload, because control flow decisions frequently happen at the boundary between CPU and GPU tasks. If you don't have a dedicated interface for expressing CPU and GPU dependent tasks along with the control flow, the overhead to partition or synchronize your heterogeneous parallelism may outweigh its performance benefit. So now I'm going to share with you some of the experience we have learned from using C++ to handle large-scale parallel application. Hopefully, our experience can contribute to making CPP more amenable to heterogeneous parallelism. Parallel computing is never standalone. It beats nothing if it doesn't apply. No one will buy the parallel computing tool without application. We must bring parallelism to practice and apply it to application. Given a tremendous amount of application, I don't believe a single model or API can express all parallelism. We need multiple CPP experts in parallel computing because each of them has their own, expertise in certain application. For example, we cannot rely on a single super powerful language or compiler to parallelize everything for us. Otherwise, the scalability becomes an issue. On the other hand, we cannot rely on heroic programmer, right, and ask them to do everything such as scheduling, concurrency control, workload partition for us. There's no CPP man in the Marvel. We need library, runtime, models to assist developer with parallelization detail. Here is how I think about the current status of C++ parallelism in existing tool. For me, C++ parallelism is still very primitive. A stu thread is very powerful, but it's considered very low level. You can use stu async to launch a task asynchronously, but there's no way for you to describe dependency between the launch tasks, which turns out to be the more important thing. There are no easy way to describe control flow parallelism using CPP. And if you look at the C++ 17 parallel STL, the only possible parallel infrastructure you may use is box synchronous parallelism, right? You run something sequential first, and you reach the parallel region, and you fork multiple threads to run that parallel algorithm. And then you join together when the control flow decision need to be made, and you synchronize all those parallel work, moving on to the next sequential block and repeat this box synchronous parallelism over and over. Also, there are no standard way to offload tasks to accelerators such as GPU. Existing third-party tools have enabled the vast success in the parallel computing. I really, really appreciate that, and I learned a lot from all this effort. But what I found is they lack an easy and express interface for parallelism that can be achieved by leveraging the power of modern C++. There are no efficient mechanism for modeling control flow. Most libraries are based on direct acyclic graph, and they do not anticipate cycle. When control flow happens, it goes back to sequential flow, right? So finally, according to our research, existing runtime lack an efficient executor for heterogeneous tasking. They are good at either CPU or GPU focused workload, but rarely both simultaneously. To sum up, we have presented Taskflow as a general purpose parallel tasking tool. It introduces a simple, efficient, and transparent tasking model for C++ developer to quickly write parallel program using minimal programming effort. We also talk about the general idea about our heterogeneous work-stealing executor and demonstrated the performance in large-scale machine learning and VLSI CAD application. There are many excellent efforts from the C++ community on parallelism. Taskflow is not to replace anyone, but to complement the current state of the art and address their limitation on the task graph parallelism by leveraging the power of modern C++. We are very, very open to collaboration, and we believe collaborative effort is the only way to make C++ amenable to parallel computing. Right now, we are based on CUDA for GPU tasking for various reasons. But we definitely want to integrate OpenCL, SQL, BPCPP, and so on. We want to provide more high-level algorithm like the thrust library, so developer can easily describe common parallel application and algorithm and integrate them into control flow and form a single Taskflow graph. If you ever use Taskflow, please let us know. We want to learn from you, and we want to grow the real use cases. I would like to take this chance to say thank you to all the users, and thank you CPPCon for giving us this great opportunity to share our experience with many, many excellent CPP developers. There are quite a few people using Taskflow right now. I'm very grateful for tremendously useful feedback from users. Thank you. Again, I'm very open to collaboration, whether you are interested in using Taskflow, understanding more technical details, or having me to present some technical innovation of Taskflow in your organization so we can talk about more CPP and heterogeneous parallelism. Here is my email. Feel free to ask me any question. You can also find more detail about Taskflow at this GitHub link. With that, I'm going to cut here. Thank you very much for your participation. I'll be happy to take any question.
Hello, Tsung-Wei.
Yes.
Yeah, we have a couple of questions from the remote. I posted in the comment section, so you can check. And there's still 3 slides delay on their end, but you can start replying those questions in the comment section.
Remo, you mean I need to go back to Remo?
No, you don't need to go back. Stick to the StreamYard.
Okay, I saw that.
Yep. Yeah, remote audience still in the page, like 3
Yeah,
pages.
I got quite a few questions. I probably will not be able to answer all of them, but I will stay in a remote Zoom, and you can definitely find me in the table on the first floor. So the first question is, what version of C++ is required? Right now, you need CPP 14, C++ 14. That is the minimum standard we require. So second question, how does Taskflow respond to being given a circular dependency ordering in large system? How would issues resulting from cycle being debugged? Well, like I say, we use condition tests that allows you to describe control flow, and the control flow can be iterative. In that case, you will describe cycle in your test flow. But the thing is, you need to make sure, right now it's user's responsibility to make sure, based on our test level scheduling, only one task can enter that cycle at one time. For example, if you have a nested cycle, it turns out there is a dependency join together between these two cycles, then the scheduler will resolve undefined behavior. Unless the holding condition and the CIDIC conditional dependency is strictly imposed by your application level algorithm. How would issue resulting from cycle being debugged? That is a really, really good question. Right now, the way we debug the cycle is we visualize the graph. You can dump the test flow graph and visualize it. But of course, in the future, we may try to, like I say in the presentation, we want to come up with some library, some other functionality that can help you diagnose a running graph at both programming time and runtime. So I got another question from Michael Huang. Would you consider doing this with a SQL? Of course, like I mentioned in the conclusion, right now we are using CUDA as our graph interface. I definitely want to have more capability. I want to support OpenCL, and definitely the SQL, the Unified Programming Interface, will be the great opportunity for me to integrate. And maybe we should talk about that offline. And the next question is it possible for users to define their own flows without inheritance and have Taskflow work with them? I'm not quite sure what you mean by inheritance. Are you talking about composition or inheritance? Maybe we can talk about this offline. You can find me at the table. So the next question is it possible for users to define their own flows with, oh, sorry, that's the same question again. Let me see. What modification, if any, are required for non-closure callables function pointer function object to emplace them to a task flow? Well, we do not. So Taskflow only handle tasking. We do not handle data abstraction. We do not handle memory. So everything you are familiar with written CPP using lambda closure function objects is all applicable to Taskflow because we do not provide another abstraction over them. We only deal with tasking. So I don't think there will be any modification for you to modify this non-closure callable, like a function pointer or function object. Because by default, as long as the task is the callable object, you can place it into Taskflow. So the next question is, can Taskflow be used to parallelize pipeline stages in a streaming computation? That is an excellent question. We have lots of issues on our GitHub, especially from the multimedia gaming industry, asking us to provide a pipeline capability. And the answer to this is right now we do not have this capability, but we are working on that. And we want to come up with a more general interface that you describe a task flow, and you can specify the data stream, and you can pipeline this stream across the task flow instead of a linear chain of operation. So then the entire pipeline task flow graph will become more general. But that requires lots of modification of the current facility, and more importantly, how we schedule them. I think I'm a little bit running out of time. Maybe we should stop here, and I will find a table on the first floor in the Remo, and you guys are definitely feel free to come reach out to me. Does it work, my host?
Yes.
Okay, so I will close.
Yes, so you will exit the StreamYard, and we will see in the zone. Yeah.
All right, bye-bye, guys.